Hello, y'all. Darrell Lee Berry Jr. back with some more graduate level physics. Going to do some classical mechanical problems with Lagrangians and eventually multipliers. I should have enough time. I'll see. And we'll go ahead and start with one in Bowles, the same book, Classical Mechanics by Goldstein, Poole, and Safko. And it's this problem that's showing on our screen right there. A hoop of uniform mass m and radius r rolls without slipping on a fixed cylinder of radius r as shown in the figure. The only external force is that of gravity. If the smaller cylinder starts to roll from rest on top of the bigger cylinder, use the method of Lagrangians multipliers to find the point at which the hoop falls off. So we'll start actually with Lagrangians multipliers. And I'll be utilizing the solutions to make sure I get everything properly. So this is sort of my review. And this is what, 2.14? So, and I'll be checking the chat, the live chat. So if anybody wants to ask a question or what have you, go ahead and drop a line. And I'll be sure to respond. So I have everything set up properly, I think. So first I'll go ahead and draw the problem. So we have a hoop here. The radius is big R. We have a small hoop. It's going to be rolling off this way. The radius is R. The only force is gravity. We want to know when it's going to fall off. So pressure made line the potential zero because we know that in order to do a Lagrangian, to get the early Lagrange equations, we have L equals T minus V. So we're going to need the potential energy, we're going to need the kinetic energy, and we have to set a baseline from which to determine the potential energy. Adding or subtracting a constant from the potential energy does not change the physics. It just alters the math, how the math works a bit. But, if you drop a ball from 50 feet, it'll reach the same speed at zero, whether you call 50 feet zero or whether you call the ground zero. Doesn't matter what you call them. The math will look a bit different, but it'll give you the same answer regardless. So the first thing, so it says it rolls without slipping, fixed cylinder. So if it rolls without slipping, I think that's fair enough to say it's going to stay in 2 dimensions. So it started with kinetic energy. So we have 1/2 mx dot squared plus 1/2 my dot squared. The upper wheel is going to be rolling. So that's going to cause some angular momentum and some kinetic energy of the spin. So if I were to call this angle phi, we know that, and you say this is a hoop, uniform hoop of mass m. And welcome who joined. You could drop a line if you have any questions. You're watching a live chat, like and subscribe if you haven't. So the hoop should have I want to make sure I go through all the steps as a moment of inertia. If I remember right, I for a hoop, which moment of inertia, is 1/2 mr squared. Let me check on that. So these things are pretty stable. A hoop is a hoop is a hoop. Yep. It's not even 1/2 for a hoop about an axis on its edge. So it's 1/2 mr squared is the actual one. Just mr squared is a moment of inertia for that. So let me see why if you put 1/2 of mr squared for the moment of inertia, the angle is going to change. So actually check my own notes because I actually put a lot of detail in my explanations. Let me see if I could parse out what detail I put for this problem here. So what I have is plus 1/2 I omega squared. So I think that's what's going on so this is the roll of the hoop. The moment of inertia for the hoop is mr squared. But what happens is I ends up being taking the place of sort of the mass. So this is like the moment of inertia is similar to the mass component, and the angular velocity is taking the place of the velocity. So we have mr squared kilograms meter squared. Yep, so that's what it is. So kinetic energy is joules, like the units are joules, which is kilograms meter squared over second squared. The M provides the kilograms. The mass from the moment of inertia. The R squared provides the meter squared, and the angular rotation provides the radians per second squared, and radians is unitless, so that doesn't have an impact. And then we have the last term. So we have the first term is the hoop as a whole movement. So we can say the center of mass moving. This is the hoop rolling. And then we have the third term, 1/2 ma squared phi. So I don't seem to have an equivalent of the, oh, I see. So those are the radial. So R dot so I mixed up this one. So we call this A squared R squared. We have M R squared. I'm not seeing where that one comes in. Maybe we did ours slightly differently. Let me take a look and see what equations she gets. So she gets the same answer as I got. Let me confirm. Yeah, 60 degrees. So there's always multiple ways to do problems. I'm going to try one more time to see if I can map exactly how I did it on how she did it. And she gave me tips on how I did it the first time. It still seems like she did it slightly differently, or maybe I'm just at a different step than hers. That could be what it is. So I'm gonna find a line that matches pretty much what she has. It looks like I did find that line. So the omega squared is 5. Let me actually see if I can follow my logic and map it to hers eventually. So the way I'm looking at this is we have the full height. Actually, let's stick with kinetic energy first. So for kinetic energy, we have basically three components: the movement of the center of mass. So the movement of the center of mass of the smaller hoop. And let me put R in the same place and call this theta. We have the roll of the hoop. And then we have the radial motion of hoop. So in other words, the hoop is moving down in this direction. That's 1. We have that the hoop is rolling like this as it goes down. That's 2. And we have that the hoop can basically move upward and move outward. Whether or not it does is a different story. But we have to note that it can potentially move upwards and outwards like that. So what I have for these is 1/2 m, and the hoop, when it moves across this part here, we'll call this part S. Like when it moves across this distance that signifies the movement across theta, we'll call that S dot squared. Similar to how if it's moving across the ground and the ground is labeled X, call it 1/2 mx squared. For the roll of the hoop, we have 1/2 moment of inertia, omega squared. So we have 1/2 the moment of inertia, whatever the moment of inertia that shape is, omega squared. And for the radial motion, we have 1/2 m r dot squared. As moving up or out, and so on and so forth. And really, the r dot r equals square root of x squared plus y squared. So we're basically just using polar coordinates for that, right? So you can simplify like we did earlier, and we know that I for hoop is mr squared. And in this case, the m provides the mass kilograms, and r squared gives the, r squared gives the meters. The angle squared gives the second squared, so kilograms meters per second squared, that's joules. And mr squared will stay the same. Another thing we can recognize is that omega squared is going to be phi dot squared. So the angular velocity is how the angle changes. So we can replace angular velocity with literally the velocity of the angle. That's just an aside. So we have T is 1/2 ms dot squared plus 1/2 mr squared phi dot squared plus 1/2 mr dot squared. Another thing we can do is put S in terms of theta. So this is the movement of the center of mass of the hoop across S, and S equals theta big R. Hold up. So one thing I'm missing here It's the center of mass and center of mass. So I have to use the distance to the center of mass. So this is where we need to get the height then. So the full distance is going to be r plus r for the complete distance. And we'll call that h. So the maximum distance, the maximum height is going to be r plus r. And we also know that that distance won't change. So there will always be a straight line from the center of mass of the big one to the center of mass of the smaller one. And wherever that is going to be h. So we can say that S equals h theta. So S dot equals h theta dot, since h is not going to change. So S dot squared equals h squared theta dot squared. So we have this equals 1/2 m h squared theta dot squared. This is the movement of the center of mass of the hoop, which has to take into account from the center of the big circle to the center of the small circle. So we have h plus mr squared phi dot squared. This takes care of the roll of the hoop. So that's why the angle is going to be phi, because the roll of the small hoop takes care of phi. The hoop overall is moving around the big hoop. So its movement as a whole is going to be with the angle theta. And then we have the radial distance in the xy plane, whether it goes up or down and so forth, which will happen when it rolls off. Right, so that should be our kinetic energy, all the points that we need, very simply. Oh, and I noticed that I swapped the radial one for h. Right? So since h equals r plus big R, if r changes, then h changes. We can look at it that way, because it'll be h, it'll be r plus r dot, which is going to be h dot. And actually, it really is not even r dot. So really what I should do then is because r is not changing because the size of the hoop remains the same. So what has to happen is even this is h from the start. So the radial motion deals with whether it goes separate down from h. And welcome who's joining. If you have any questions, let me know. I'm doing a Lagrangian problem with multipliers for a hoop rolling on the top of another hoop. I'm going to calculate when the small hoop falls off. Complicated math, complicated physics, but we shall work it out. So what's really happening is h plus r is fixed. And if the hoop raises or lowers, then this is really going to be r plus h plus some change. What do I call this? Change in r prime. So that's going to be h prime. So if the hoop, let's say the small hoop were to, when it falls off here and is rolling down, this big distance is going to change. We're going to put this in terms of h, and that's going to cover this entire thing changing. So that's why from there I should have put h on this whole thing, put a radial distance, because the size of the big hoop is not going to change. The size of the small hoop is not going to change. But what's going to change is the overall distance between the big hoop and the small hoop, which is going to cause another distance variable to appear, and overall h is going to be changing. So we have that. So now I think we have our kinetic energy. I think I explained all the details for that. 1/2 m h squared theta dot squared plus 1/2 m r squared theta dot squared plus 1/2 m h dot squared. All right, so we got that. Next thing we needed to do is get the potential energy to figure out the Lagrangian. We know generally that's going to always be mgh, and h is probably a bad variable to use now, so I'm using h for that. Well, it is h because I set my potential to be 0 in the center of the bottom hoop, and the center of mass of the top hoop is h distance away. So yeah, so h actually does work here. So mgh is our general potential energy. Now the thing is, while the small hoop is rolling down the big hoop, this angle theta will determine how much is accounted for. So if the big hoop is there, the small hoop is there, this is my plane, this is going to be theta, and the vertical is going to be here. So as we can see from our trigonometry, we have sine, so this is h, sine of theta equals h, or hold up, let me call this something else. What did I call it before? No, it is h, because h is the full distance here. H, sine of theta equals this distance. I'll call this x over h. So x equals h sine theta. Now if I'm doing that properly, let me think. Oh, you know what? I mean, technically that'll work, but I want to keep the same setup that I had last time. The last time I actually counted the angle from the vertical, which makes sense because the ball is rolling from the vertical position. Therefore, like the small ball starts here. So here, theta equals 0. And here, theta equals theta. So if I want the height here, and this is theta, this will actually be cosine. So x equals, so cosine of theta equals x over h. And this is x, the height, because we're coming in this direction like this since the sphere starts on the top. So basically we're using like a polar angle. So cosine of theta is x over h. So x, which is the height we want, is h cosine theta. So that means that I can input that where, that means the potential energy is going to be mgh cosine theta. Okay, now we're getting somewhere. All right, so now we can move to the Lagrangian. That's the first part. So those who are watching, let me know if you have any questions. I'll give you a moment to let me know if you have any questions about what I did so far. And while I'm waiting for questions, you can type in a live chat. I'll just review what I did. So I'm trying to get the Lagrangian, which is T minus V, kinetic energy minus potential energy. I recognize that there's 3 points of kinetic energy in the system. There's the entire ball on the top rolling down the smaller sphere. There's the roll of the hoop has its kinetic energy. And there's the fact that the entire upper hoop can move off the sphere. It can move in 3 dimensions or 2 dimensions. Like when it rolls off, it'll roll off that way. So we have basically the motion of the center of mass of the hoop radially. We have as my professor called it, we have the motion of the center of mass as it moves around the big hoop. And we have the roll of the small hoop, each of these 3 kinetic energies. So the movement of the center of mass of the small hoop, that is used as if it was just moving along the ground, x, 1/2 mv squared, 1/2 ms squared. The ground in this case is s. The roll of the hoop, we have to use for the kinetic energy, the moment of inertia and the angular velocity squared. So I have 1/2 moment of inertia I of hoop, angular velocity squared, and I guess the kinetic energy for the roll of the hoop. And then we have the radial motion of the hoop moving outward, which means that the full length, the maximum height will change, which is h. So 1/2 mh dot squared. Because that whole radial distance, we're going to put it in terms of the whole radial distance, which will make it simpler. And we don't actually know we don't know what h is either, but we want to put it in terms of the larger scope. To simplify my s, I put this in terms of the larger scope as well, h and theta, to limit my variables. So s is h theta as it moves across the big sphere. S dot is h theta dot. So s dot squared is h squared theta dot squared. So we substituted that here. We input what the moment of inertia is for a hoop, which is mr squared. We recognize that angular velocity is how the angle is changing. So I'll put that here as phi dot squared. And we just carry the radial motion down. So that's why we got kinetic energy. Potential energy is generally going to be mgh. So what I need to do is put h in terms of the angle, because the potential energy here at the top will be mgh, where it's starting. But it's rolling that way. So the potential energy will lessen. So since it's starting at the top, I'm going to call that my 0 angle. And going to the right using trigonometry, this height here is going to be cosine of theta The angle for the big hoop as it's, going around the big hoop. The angle cosine theta is x, the height over h. The hypotenuse, which stays the same as long as it's in contact. So x, that vertical height, is going to change according to h cosine theta. So I just plug that in for h. So maybe I should call this h prime for the first one. All right, so that's what we did so far. I don't see any questions. You can still let me know if any questions come up. So now we can do the Lagrangian. We can see that L equals T minus V, which equals 1/2 m h squared theta dot squared, which is the motion of the small hoop, the center of mass around the big hoop, plus 1/2 m r squared phi dot squared, which is the kinetic energy from the rolling of the hoop, plus 1/2 m h dot squared, which is the fact that it can move in 2 dimensions, like when it falls off, minus mgh cosine theta, which is the potential energy as it changes as the ball starts to roll off the larger hoop. So now we have the Lagrangian, and we have to take 3 for the Lagrange equations. So the way I have it here, the Lagrangian is a function of h and h dot, theta and theta dot, phi and phi dot. So that's another reason why we put things in terms of everything we can. M is a constant, the mass is constant, h may change, r is a constant, and we don't have to even put big R up in here. So, and it matches what I had before. So everything seems to be good. And I'll check one more time. Got that one. Got that one. Got that one. All right, everything looks good. Another thing we need to do, it said that we're using multipliers. So I need to have some equations of constraint. So we already noted one constraint, that r plus r, little r plus big R equals h. That's not going to change until it separates. So we'll call the first equation of constraint r plus r equals h. And it has to be in the form of equals 0 to work. So we have h minus r equals 0. The other constraint that we have is that basically when the sphere, the smaller sphere, is rolling around down the slope, because it's saying it rolls without slipping, looking at the book. So since, and we're doing number 14. So since it rolls without slipping, that means that the amount of distance carried by both of them will be equal. So that means that when the small hoop covers S amount of distance, it'll be some phi times little r, but that same amount of distance will be covered by theta big R. So those will be the same. And actually, hold up. It'll be the same thing covered by theta h. Would you make it more correct? And thanks for dropping a line, Sherlock. She says, keep it up. This type of content is really needed. You're certainly welcome, man. Thank you for letting me know. So I'm glad you enjoy. I'm glad it's helpful, and you can look forward to some more. So I really appreciate it. Thank you for dropping a line and saying so. And what we'll do, we'll look more closely at why this is H. So my first impulse was to think that, okay, hold on. All right. So I think I see what now this part is still a little bit strange to me. I think it's because I'm thinking about it in terms, I switched away from the center of mass again. So when this thing moves, I need to actually look at where the center of mass is. Let me make this a different color. So the center of mass will be here, the center of mass of the smaller circle. So the distance covered is not necessarily the distance on the big circle. The distance S is the distance covered by the center of mass of the small circle. So as far as the small circle, S will be transcribed by so many turns, so much angle phi times little r, and it'll etch out a certain distance. And then they have to reach, but of course that takes into account the center of mass because it's literally rolling around the hoop itself. But the next thing I need to do is look at theta in terms of the distance to the center of mass. So this is to center of mass. So that's why it has to be H. So S is transcribed by little r and phi as this little hoop rolls around the big hoop. And it's transcribed by H and theta as this entire H transcribes to theta because it has to reach up to the center of mass. So this is why I kept getting this problem wrong at first. My professor helped me out with it. I kept trying to, which I still have a habit of doing, but that's why I'm looking over the solutions as I go so I can correct it right away. I have a habit of wanting to look at each individual sphere or object. We have to always go to the center of mass of the moving object to get the full distance. So now we have that. So now we have our two constraints. And to make it go even farther, we can say that S dot equals phi dot R equals theta dot H. And we'll call this F2, our second constraint equation. So I have to think of why we did theta dot and phi dot. I didn't make a note of why we do theta and phi dots. Well, that's just because each of the equations have dots. So I would say that S is going to be transcribed when it's connected. So that's why H doesn't change to transcribe S. But since each of our equations have a dot, we'll go ahead and make that a dot because it's equal. But in this case, H doesn't change when it's connected. So in both cases, we need to go to the highest derivative while it's connected. So those are our two constraint equations. And put it into the proper form actually before I box it. We'll have phi dot R minus theta dot H equals 0. And that becomes our second constraint equation. All right, so now we have everything we need to start solving the problem. And Shannock says, so theta is where the center of the hoop and phi is. How much this hoop is fun? Let's look at that. So, and it is a bit weird, I think. So phi is how much the hoop is spun. So this I'll label phi. So as the small hoop rolls, it's spinning through phi amount of angle. And theta is really how far it moves around the big hoop. So the big hoop is stationary. It's not moving at all. So when it moves from, let's say, here to there, it moves theta amount of angles around the big hoop. And we have to use theta because the smaller hoop is smaller, phi will be bigger than theta. So we can't use phi because, let's say by the time the small hoop rolls around twice, it could still only have gotten through 1/4 of the big hoop or 1/2 of the big hoop or what have you. Let's say 1/4 of the big hoop. So to transcribe its movement around the big hoop, we have to use a theta angle to get it properly. But since we still have to go to the center of mass of the small hoop to know where it's at, we have to use theta for the big hoop because it's going around the big hoop. But we got to use a distance from the center of mass of the big hoop to the center of mass of the small hoop to transcribe S. So I can put that here. We have S is going to be theta big R. And, not big R, H, I meant to say. You still have that habit. As you can see, if I was to write this out, this is R, little r, and this is big R. Let me know if that's clear. And I'll check and see if you have a follow-up question to that. So there we go. So we have that. That's why we have the theta is changing all the way up to H. But it's going to be related to how much phi changes because even while the big hoop goes around, phi and R is going to roll enough to make that same distance. So as far as the big hoop is concerned, it can be rolling or not rolling and just moving through that angle. But as far as the small hoop, it has to roll to match up. So therefore, they're going to be equal. Awesome. Glad you get it. Glad it's clear. Now, the thing is, we have to use our multipliers, which alters the Lagrange equation. So I will say the Euler-Lagrange equation with multipliers is going to be full derivative d dt, partial Lagrangian over partial q I, and this is going to be with a dot, minus partial Lagrangian over partial q I. Then we have plus our multiplier, lambda I partial f over partial q I, and that all equals 0. So this is just our normal Euler-Lagrange equation, which I believe I derived a few videos ago. One of the videos I derived it. Hopefully I titled it Deriving the Euler-Lagrange, but I derived it like a week or two ago. How we get that. And to use the multipliers, we're basically going to use these equations of constraint rather than using them to lessen the amount of independent variables we have. And the reason why we have to do that is because we want to know when this thing is going to fall off. It actually is in the book. So we look at the problem. It says use the method of Lagrange multipliers to find the point at which the hoop falls off the cylinder. The only way we can do that is to take into account the constraint forces and find a force of constraint. And we know that force of constraint gives way when it falls off. So while the hoop is up on top, the big hoop, the normal force is matching the gravitational force and is not moving. But we know when it falls off, the force going away from the hoop is greater than the force keeping it in, so therefore it leaves. So that's why we need the multipliers to keep all the equations and not lessen the number of equations that we have. So we have to solve it like this. All right. And the coordinates, as I said before, is going to be h, theta, and theta dot. So we're going to have to do a Lagrange, order Lagrange for each of those. So I'll start with h. We'll go in that order. H, theta, and phi. So for h, we have, and I'll do 1. So let me write it in a different color. I'll do 1. I'll do 2. I'll do 3. And then I'll do 4. So that's the order that I'll do these in. So 1, we have partial L over partial H dot. So that equals, and I probably should copy the Lagrangian down so I don't have to keep scrolling up so much. So let me do that. So this is our Lagrangian here. I'm going to make it in bold. So I'm taking the partial derivative of that with respect to H dot. So I have just one H dot. So I have M H dot. Yeah, just MH dot. There's no other H dots up in there. And let me make my dots a bit bolder. I've bolded everything. We have d of dt, d dt of partial L over partial H dot. So that's going to be EMH double dot. Let's take the time derivative. For 3, we have partial L over partial H. And there is only one H. So it's going to be mg cosine theta. And for 4, we have lambda 1 times partial F over partial Q I. But it's going to be using one of the equations of constraint. Looks like here, and I forgot to ask Professor about that. I meant to ask that. Like I noticed here I'm going to use this one, but why I don't only use that one? So I have an impulse to want to use both, but I'm not sure why I picked that one. But let's just go ahead and use that one. So I have lambda, and if I take the partial derivative of that with respect to h, it's just 1. So that equals lambda, right? And I'll just call this lambda 1 since I use F1 for that one. All right. So that means if I put this all together, we have MH double dot minus mg cosine theta plus lambda 1. All right, so we have that. So we have the first of our equations. And let me check. H double dot. Hold up, I think I missed something. Hold up, what did I miss? I missed a term somewhere. Oh my gosh. I missed that there's a H here. So I did miss one of my terms. So for this H derivative, I have to take a derivative of this and that. So this is going to be so I'm going to drop the 2. So that's MH theta dot squared. And I can't forget my minus mg cosine theta. Okay, there we go. So that is everything. So now that I got my H that I missed the last time, let me check the chat. Chinook says, do you need Lagrange to solve this? I know the question specifies, but couldn't you also use energy conservation to relate the hoop speed to its drop in height? I really don't think you can do that. What specifically what this is asking, because it's asking when it falls off. And I don't know that energy will tell you when it falls off. Because I don't know that it's a matter of, well, I guess perhaps because you can get you know what I think the difficulty might be? We don't have the normal force. We know the normal force is mg. Um, yeah, I don't know. I don't know if you could use it that way. I imagine this is probably the easier way. Generally in physics, they want you to use the equation, whatever process gets you to gets you to answer the most quickly and most easily. But I don't know. I can't say I'm good with the energy waves anyway. Like that's probably one of my weakest problems right now. I'm taking a foundations class, like in order to be eligible to apply or go to the panel for my PhD. I have to show proficiency in all of undergraduate physics. So we have a course where we basically go through all of undergraduate physics in like a semester, and we have like a test almost every week. And but energy is one of my weakest parts, like potential and kinetic energy and total energy. So I have to work on that. Shenak says, then you use radial force balance with normal force. That's correct. So in this one, basically we're checking when the not necessarily when they're balanced, but when it changes. So this, how my professor explained it is, this constraint here breaks when the box falls off. So when the hoop falls off, so when the hoop falls off, H becomes H dot, and we're using that fact. We're using just that simple fact that as long as it's in contact with the big hoop, H equals little r plus big R. The moment it falls off, H does not equal big R plus little r. So that's why we're using multipliers, because we can use this equation here and use that fact. And when that breaks, then we know it doesn't work. Uh, Practically, it ends up being, to scroll up a bit, practically it ends up being similar to that. We basically get a differential equation, and we can use some math trickery to resolve into a cosine, but we'll get there, and we'll see how that's resolved. Jenny says, I'm also taking a lot of foundation classes. I was an aerospace engineer undergraduate. Awesome. So you're in grad school as well. You're in grad school for engineering right now? I was a physics and astronomy undergraduate, by the way. They have another physicist on. Well, he says he switched to physics after working in a propulsion lab and wanting to look into plasma physics. Awesome. Congratulations, man. I have a Discord. You should hop on sometime. Maybe we can study together sometime. The Discord should be showing. Is it showing? Well, I could go back to my other screen real fast. It'll show. So that's my Discord right there. You should log on. And I'm usually there. Well, I'm always there whenever I'm streaming, so you can pop on live and ask questions and listen in. And also, we could actually set up a study session sometime or something. So let me know. So you can scroll back right there and see it as always. Oh, and of course, you can find it on my website there. That's always at the top. Awesome. Let's see what we have here. We have number 2 minus number 3. So we have mh double dot minus mh theta dot squared plus mg cosine theta plus lambda 1. That's our first equation. Let me check and make sure I didn't miss anything again. Let's see here. So that looks good. mh double dot minus mh theta dot squared plus mg cosine theta plus lambda 1. That all equals 0. So now we're going to move to the, what did I say I will do next? Theta, done in a similar fashion. So we have 1 partial L over partial theta dot equals, so theta dot, let me make sure I don't miss one. Looks like I have just one theta dot. So we have mh squared theta dot d dt of partial L over partial theta dot equals mh squared theta dot dot. And we have 3 partial L over partial theta. So let me make sure I don't miss any. So far as I can tell, I have just one theta, which is here. So we have, and it's not theta t, it's just theta. So since it's not by theta t, all this says mgh sine theta with no time derivative. Let me check and make sure. Yep, mgh sine theta. And then we have 4, which is going to be lambda partial f over partial theta. And that time I used the first one again. So I use lambda 1 again. So I'll call this lambda 1a, and this is lambda 1b. So df d theta, there's no theta in the first constraint equation. So that becomes 0. So we have, well, to put this together this time, we have mh squared theta dot dot minus mgh sine theta equals 0. So that's that. Johnny says, oh, I don't think the Discord link is working. Might need to post a new one. Oh, crap. So I guess it times out after a while. Let me just share another link in chat right now. Don't mind the switch out. Let me just get out of this so it's not looking all crazy. Oh, I think I clicked the wrong thing anyway. They're going inside the server. So I'll make sure you have this right away. Invite people. Discord server link. Boom. Let me actually change it to never expire. Generate new link. Awesome. So this link here should work. And later on, I'll go in and update it into the image. Or maybe I could do it now. What did I save it at? Yeah, it's not so hard to do it right now. All I have to do is just go like that. Like that. Awesome. Thank you for letting me know. And please let me know if that one works. I have it updated as well, so everything should be good. Very quick fix. All right. So we have that one. That one seems to be worked out. Awesome. Thanks for letting me know. Appreciate it, sir. So now we go to the last equation, and then we can solve this thing, work this thing out. And I'll keep my same, hold up. I do have an H there. Why do I have an H there? Hmm. I may have made a mistake in my note, in my homework. They have, oh, you know what I did? H. All right, I'll just leave it like that. And looks like I just made a mistake on my notes. Well, even though I got to the right solution, so we'll see how this works out. So the last one I have is phi. So my 1 partial L over partial phi dot equals, all right, so I see 1 phi dot. So I have m r squared phi dot d over dt of partial L over partial phi dot equals m r squared phi double dot. Easy enough. That's 2. For 3, we'll again have partial L over partial phi. So that equals, I don't see a phi. Yep, 0. And for 4, we have lambda partial f over partial phi. So that also equals 0. Now hold up. I use F3. Did I have a third? Oh, that's what I did. I'm using 3 of them. So the third constraint I had was without the uh, dot producting it. So I call this F3. All right. So if I use the F3 one, then it's R. Then it's lambda R, lambda 3 R. Because I'm going to call this one lambda 3. So there's one without the dot product, one with the dot product, and this we can't dot product because everything will just go to 0. But the thetas and the s's can dot product. Maybe that's why I have one for this second one as well. So theta doesn't work, but theta dot works if I use lambda 3. So I'll call this lambda 3a, and I'll call this lambda 3b. So I'm going to do the theta dot one. So if I do the theta dot one, then that becomes h. And this becomes plus lambda 3b h. And this becomes mr squared theta, at least phi dot dot, minus 0 plus lambda 3b r. And let's see what I have here. Confirm everything is okay. So I have Oh, and this equals 0. So this is what I have for that equation. So that seems to be okay. For the second equation, I do have that. So that's what I was doing. I was using the, so I guess you could use any one that works. I have to remember to ask about that. I'll ask my professor about that tomorrow. Which FI to use other than trial and error. I mean, I have an exam on this stuff on Friday, so trying to get as efficient as possible. MH double dot square mg cosine theta. All right, so all of our equations, they match what I had before. All right, so there we go. And Shanak says, I don't think you're sharing the queue. Oh, sorry, crap. I forgot to push back. Sorry about that. I do that sometimes when I move to do something else. So what I was doing before, which you all saw, was in the previous ones, I just did the theta one. Sorry about forgetting to change. And Shanak says, what field do you hope to do research in? Astronomy, stars. So I have a bachelor's in physics, a bachelor's in astronomy. Both I had some honors. And because I was interested in astronomy and the physics gives me a good foundation. So right now I'm doing research into stars. I'm modeling stars and getting a better understanding of stars so we can use them as better distance measurements. So that's what I'm doing now. So my favorite thing about astronomy is stars. So in my undergraduate, I did research into star clusters, where I was discovering properties of how properties in these star clusters relate to each other, like distance from each other, like position, like rotation, luminosity, not luminosity, but spectral type. So I investigated the Persepi star cluster. And Shanak said, that's very cool. What do you use to model stars? Is there a lot of programming involved in that? I mean, I use this program called MESA. It's an open source program. I'm just finding this kind of difficult to work with. It's a very complicated program. I mean, it has a lot out the box. It's not like it uses Fortran, so I'm learning Fortran. You don't have to learn it straight up, but it takes Fortran codes. And maybe one day I'll make a video about that. Maybe I'll make a video and show my research. I miss what I usually do. I usually show what research I'm doing. So thanks for reminding me, bringing that up. I'll do a video. Probably, maybe that could even be in my next week's video. Maybe I'll talk about the research I'm doing and doing MESA. I'll see. Awesome. Yeah. Thanks. I'm glad you'll appreciate that. So I'll make sure I set that up. I'll schedule that. And if it's not on a if it's not on a Saturday, it'll be on one day. Of course, I'm doing a lot now because I'm having a test coming up. But I plan on still being more consistent. But it's cool. It's a good program. It's just, I was shaking my head because I was trying to, like, we have a meeting on Wednesday with my advisor, who's going to be my advisor. He's not my advisor officially, but until you actually start working on your PhD, but I'm sure he will be. He's a star person here and I'm doing stars. We work together a lot. He's leading my research right now. And I was supposed to model a star with a more accurate concentration of helium and hydrogen, but I just could not get that damn thing to change its concentration. I just couldn't get it to do it. I tried every way I could, so I'll have to see what I have to do. They just have so much in it. It's probably just one thing I have to figure out how to change, but I couldn't get it done today. So, but I was able to model change the mass of a star a few weeks ago and model it. But I'll work on it. I'll get it done. Maybe that's what I'll show y'all next week if I get it done by next week. So we got this. We got our equations, 3 equations. Let's see what we can do next. So the next thing I need to do is, and actually let me go ahead and do like I did before and just put all the equations in one place. So we got them like all spread out. So we have the first one here, mh double dot minus mh dot theta dot squared plus mg cosine theta plus lambda 1a. And I guess I don't need an A on that because I only use lambda 1 once. We have the second equation, Euler Lagrange equation, which is mh squared theta double dot mgh sine theta plus lambda 3bh. We have mr squared phi double dot plus r lambda 3b equals 0. And we have our constraint equations. So we're going to have to use these equations to solve this system of equations. So what we actually have now is a system of equations with several unknowns. So that's why we need several equations to solve it. So what we're going to do is we're going to manipulate these equations and solve for the unknowns. And then we can cancel some things out and we'll have a nice trigonometric equation where we can solve for the angle at which this thing will fall off. So we're almost to the point of wrapping this up, and I'll go ahead and call it a night. All right, so this is what we're looking at. And our product should make all of these equal to 0. Let me do that. So this will be that minus that equals 0. And this will be, I'll just do it on this side, 0 equals that minus that. Okay, so we got that. So first thing, so these matrix I learned from my professor. And he says, I've always wondered how things like the Chandrasekhar and Oppenheimer-Volkov limits were proven. There's no real experiment you can do. Right? That's not true. Because what happens is we could observe these stars very, very, I guess I can't say very frequently, but frequently enough, because binary stars are probably the most abundant type of stars in the universe that we know of. Most stars appear to be binary or more, but most of them seem to be binary. And the Chandrasekhar limit happens usually when like a neutron star is siphoning matter from a nearby star. And because it's a binary star, that's how we can get the masses of stars. I don't know if there's another way we can directly get the mass of a star. So the very nature of a type 1a supernova lends itself to understanding the Chandrasekhar limit because we can get the mass so readily. Now, one of the reasons why I'm doing the work I'm doing, which is because my advisor doesn't doing that kind of work, is because we know that the distances can be improved. So we're trying to improve those distances. So there may be some variation in error on the distances, but generally, we can see and observe with a binary system that that supernova it goes nova when it's around 1.3, 1.4 solar masses. And Chandrasekhar says how defined are the mass limits? I know for Chandrasekhar it's 3 solar masses, and for OV it's like 8. Are these super defined or more of a spectrum? Yeah, I mean there is some variation because like 2 stars can collide and end up exploding when they're bigger. And my advisor was saying that one of the reasons why we have to do our work now is because some of the distances we're starting to learn could be a bit off. Like there can be more fine tuning on the distances because of various as we get better instrumentation, we can see differences in these stars that we couldn't have seen before. So there are some differences like in the light curve that we couldn't see before, that we know that there's more variation that we thought before. So it's still around 1.3, 1.4, but there is some variation. And that variation gives us a variation in distance. And thus the variation in distance will give us a variation in the other calculations. So I don't remember the details. My advisor, he often gives us all of these. He's like an expert on stars, Dr. Keel. So every time we have a meeting, he usually gives us some background information on stars. And one week he talked about that, about the differences that we're going to sharpen up with our work. That's right. That's right. Pretty much just the light that's emitted from the star, and the shape it takes as far as the frequencies that's emitted and the strength in various frequencies. So, the light curves of these stars are very similar. That's how we can use them for distance measurements. But we're finding that there are some differences in the light curves. It means there's differences in compositions or differences in this or that. That's throwing off some of the calculations a little bit. So, you know, maybe it might be 1.5 to 1.3 instead of just 1.3 or 1.4. We're working on sharpening it up. So I don't know what in the end my PhD will be about, but I know it's going to have something to do with that. What I'll do, by the way, I'll number these equations the same thing that I numbered them before. It'll help me follow in my notes. I call these 13, 12, 13, 14. I call this one 15. And I call this one 16. And just in case, I'll call this one 17. So that's what I'm going to do. I'm going to take 16 and want to DDT it. So that's going to be phi theta double dot H plus phi double dot R. We have this. And what I'm going to do is solve for phi double dot, which is going to be phi double dot H over R. And what I can do with this is insert this into 14. So remember, I'm trying to get some equations of motion that I could then simplify. So if I plug this into 14, what's the best way to note this? I'll just type it, insert into 14. So if I insert this into 14, we can see how I have mr squared theta double dot H over R plus lambda 3VR equals 0. So I have mr squared, mr theta double dot H equals negative lambda 3BR. And I dropped a negative, it seems like. Did I drop a negative? I think I did. Oh, keep going and see what I did. So I'm going to cancel out that. Okay. So when I cancel out this R, now I have lambda 3b equals m theta double dot H. And I'm actually going to call this 17. So I'm going to rename this to 11. I'm going to call this 17 like I called it before. So I have this. Now I'm going to insert this into 13. All right, so now it's getting crazy, getting busy. So let me copy 13 down first. So we have m, okay, that's why, because I'm going to replace lambda 3. So we have mh squared theta dot dot minus mgh sine theta plus m theta dot dot h squared. When I insert that in, So almost there. And this equals 0. So it's still, even though I cut off my 0, I cut off it here, but this whole thing equals 0. So what I can do now is solve for theta dot. And I see that I have 2mh squared theta dot dot equals mgh sine theta. And I could cancel out a mass and an h there. So I have an h here. So that means that I have theta double dot equals g over 2h sine theta. All right, so we have that. And this matches an equation in one of the textbooks I looked at to help me with these problems. All right, almost there. And now we're going to get to a very sick mat trick. This mat trick is deep that I learned from my professor that's going to come up in a moment. So, all right, so check this out. Right now I have theta double dot g over 2h sine theta. And one thing that we don't know is what theta dot is. So, for instance, looking at number 12, we don't know what theta dot is. So we need to find the equation. We need to solve for theta dot squared is right here in order to finish solving this thing. We don't know what that is. But if I were to do this, you also take a derivative of theta dot squared, I would end up with 2 theta dot theta dot dot. I'll take the derivative of that. And now I have what I have here. So we need to solve for theta dot squared. I don't know what theta dot squared is. I'm trying to simplify this equation. I do have theta double dot. I can see what theta double dot means in terms of sine. So now I'm going to turn my theta dot into theta double dot so I can solve for it. So I'm going to plug in my theta double dot here. So now I have 2 theta dot g over 2h sine theta. Which means if I was to cancel some things out of it, I have theta dot g over h sine theta. And one thing we notice is if I change this around a bit, we know that if we take a derivative of sine, it ends up being like we take an integral of a derivative with a function inside of it, we get a function back and the derivative of whatever is inside of it. So if I take a derivative of sine or integral of sine, what do I get? If I take an integral of sine, I get cosine. So what I can do is I can say this is the same thing as g over h is a constant. We know if I take an integral of a derivative, it's the same thing. So if I take an integral of d dt of 1 minus cosine theta, that's the same thing as saying theta dot, at least hold up, not the integral yet. If I take the derivative of that, the integral to come later, that's the same thing as getting what I had there. So in other words, d dt of 1 minus cosine theta, where theta is a function of t, is the same thing as sine theta, theta dot. So those two are the same. These two are equal. So what I'm going to do now is, remember all of this stuff is equal, so I'm going to bring this down. So now I have d of dt of theta squared dot equals g over h d dt 1 minus cosine theta. So then, if I take an integral of both of these, now I know that theta dot squared equals the integral g over h of d of dt 1 minus cosine theta. And that's another question I forgot to ask my professor. Why we do 1? Oh, I said I wrote it in the homework. So in my homework, when I turned this in, I asked her, why do I put 1? Because 1 is just a constant. You take a derivative of 0, it doesn't affect anything. But if I don't put that 1 there, the problem doesn't come out properly. And you get an answer, but you get the wrong answer. Your answer is too big. So there must be some reason why you would know to do that. I don't know. I guess you just got to get used to destroying random constants and things. All right, so we have this metric. So going back to where we're going to plug this in at. We're going to plug this into here. This equation here, 12. So now that I solved for that, and let me make sure I didn't miss any steps. First, let me solve for lambda 1. Lambda 1 equals mh theta dot squared minus mg cosine theta minus mh double dot. That looks good. Cosine theta. Where does my mg double h go? Oh, so this is going to equal 0 because basically what we're trying to do is we're trying to solve for when that breaks. So first we're going to assume that it's working. We're going to assume that it's working right now. So I guess we can say, if I was to put this in context, our constraint equation was h equals r plus big R. This is constant while in contact, while the small circle is touching the big circle. If I was to take h dot, R doesn't change, big R doesn't change, so that equals 0 because the size of the hoops don't change. So R double dot equals 0 as well because the size of the hoops don't change. Because remember when I defined it, I took the change to be in addition to these two. I remember where I wrote it at now. I know I wrote it somewhere. Or maybe it was in the side and I erased it. Yeah, right here. So we'll take the change in h to be some thing in addition that's making that change. But this constraint equation doesn't have that thing in addition, so it's going to be 0. So therefore that zeroes out. So we have lambda 1 equals mh theta dot squared minus mg cosine theta. We know what the unknown is. We have theta dot squared is going to be this squared. Hold up. Okay. So let me copy this whole thing down. So that was just to prove that they equal the same thing. But if I don't take the integrals of either side of them, did I erase it? I shouldn't have. No. So if I don't take the integral of either side of them, then they equal that. There's a ddt on either side, so I could cancel that. So then we can say that theta dot squared equals g over h, 1 minus cosine theta. So now I can plug that in. So basically I'm just, I could cancel the integral and not take an integral of anything. I could cancel the ddt because it's happening on both sides. So these differentials can be treated as if they're, variables and things like that. So that cancels out. And then I have lambda 1 equals mh g over h 1 minus cosine theta minus mg cosine theta. And that all equals 0. So remember, this whole equation equals 0, even though I forget to write the 0 sometimes. No, hold up. Oh, okay. The 0 is something else. So basically, we're setting it equal to 0 because we're basically making that constraint equation be a constraint. So we're going to find out the limit at which it changes. So it's kind of like if that big hoop and the small hoop are still in contact, at the point that it breaks off, the change happens from a broken, consistent constraint to a broken constraint. So I guess it could be considered like an extremum. Like if you're taking the extremum of a curve, you set the first derivative to 0, and the extremum is that. I guess that's how I think about this process right here. I'm setting this equal to 0 in the similar sense of I'm going to find the extremum where the change happens, except the change is where this small circle falls off the big circle. So when I find out where that 0 happens, that's going to give me that exact angle of the change, similar to the exact point where the extremum is, the minimum is, or the maximum is on this curve. So now I have the h's are going to cancel. So I have mg 1 minus cosine theta minus mg cosine theta equals 0. And that looks good. So if I was to distribute this out, I would have mg 1 minus cosine theta. And there's also a minus cosine theta here equals 0. So all I did was just extract out the mg and put them both on the outside. So now I have, I could divide the mg over. So the mg could cancel if I divide both sides by mg because they are constants. So I can see I have 1 minus 2 cosine theta equals 0. So I have 1 equals 2 cosine theta almost to the end. So I have cosine theta equals 1/2. And now I have theta equals cosine inverse 1/2. And if you put that in your calculator, you'll see that theta equals 60 degrees or pi over 3. So using the constraint equation, setting it equal to 0 of when that change is happening, similar to a minima, we know that if you have a big sphere of radius big R, or a hoop, and a small hoop of radius little r, and is rolling down the side under only the force of gravity, we know that when it reaches 60 degrees, so if I come from the top, what, 369, so yeah, about right there, the hoop will fall off and lose contact with the big hoop at that point. So there you go. All of that works to get that simple answer. So let me know, Shanak, if you have any questions. And you can let me know if I'm pronouncing your name incorrectly as well. So it seems like Shanak, but it might be with a different intonation. I'd be happy to make sure I pronounce it correctly. You can let me know if you have any questions on this before I close up, or any questions on stars or anything. I can spend a few minutes and just answer some general questions while I log off and get a snack and get something to eat. Awesome. Sounds good. Thank you for dropping the line. It was good talking to you. And I'll definitely do that and make a video on the research I'm doing now. I need to make sure that my professor or my advisor told me that's all I'm going to having problems changing the masses of composition of the stars. They're like, well, just do this if you're having difficulty changing the composition. Just make sure you have something next week. Just try different masses. So, because I could change the masses. So he was like, well, I'm basically studying R Lyra stars. There's a certain type of star that's a variable star that we could use for a good distance measure. We say let's try different masses of the R Lyra star, like maybe 0.5 solar masses, 0.65, and 0.8. And if I can't get the composition, I can at least, we could look at the physics in that. But I'll see if I can get the composition as well. So I have to just figure out what to change. But awesome, Shanak, good seeing you. And I'm sure I'll be back tomorrow because I have my exam on Friday. And I only went through one out of the, 4 problems in this homework. So I'm sure I'll be back. And Shanak says, have you looked at the turbulent convection in stars, like how it affects characteristics? I mean, a little bit. Because I know, like, from my undergraduate research, I looked into sunspots because at first I actually started measuring the rotation of the sun. So I learned about sunspots and saw how the magnetic fields play along with that. And but I know that some stars, I could share again, some stars are made like this, depending on the size and mass and all that stuff, where pretty much the whole thing is a convection zone. And some of them, they have like a small convection zone like this. So I'm pretty sure it has an effect on the rate of rotation we observe in a star, because technically we only observe in the surface of the star rotate. I wonder if the inside rotates the same pace. But I can't say I looked into it in detail, just enough to get an idea of what's going on with the surface as I was measuring the rotation. But then when I went to I was going to actually get more involved in measuring the rotation. And my advisor at the time said, we need to do something more complicated. So I looked into clusters of stars. And that's how I started that whole deal with looking at the properties of stars and clusters. And I looked at the Persephone cluster and arranged an understanding of that. I could believe it. Magnohydrodynamics. Stars are interesting, man. It's interesting to think how it starts off as just this random collection of gas floating around, and gravity takes hold and thermal pressure takes hold, and voila, you have an entity that on one sense is still just a collection of gases, but on another sense, the physics involved in such a massive thing collapsing just causes so many things to happen. Is thermonuclear, basically detonations happening and all kind of stuff. One of my friends double majored in mechanical engineering and applied physics and did some undergrad research in this. Awesome, man. Should let him know about the channel. I'd like to talk to him as well. Maybe you could join the Discord too. You can start developing a nice little community, a nice physics community, astronomy community. Awesome, man. Good chatting with you. I hope to see you tomorrow. I don't know what time it'll be, but I imagine it'll be around 2 hours earlier from now. And I'll go through a few more problems. There will be some more Lagrangian with or without a multiplier. I'll probably do one without a multiplier tomorrow. Yes, thanks. I'm actually in Central Time, so it's like 11:30 right now, but I'm usually up late. So thanks, man. You have a good night as well. I'll look for you tomorrow if you're available, or next time whenever I see you. Hope to see you again. Everybody else who is watching, have a good one. Feel free to drop online as well. Like and subscribe if you haven't already. Help me get to 1,000 subscribers. I'll see y'all next time. Good chatting as well.